Hi, my name is Tommy Chusan. I'm a graduate student from Georgia Institute of Technology, also known as Georgia Tech. I'm going to give presentation about exposing congestion attack on emerging connected vehicle-based traffic signal control. The presentation is based on the original paper from researchers of University of Michigan. It was presented at NDSS Symposium on February 2018 in San Diego, California. You can view and download the research paper from this link. Some introductions for the topic today. Connected vehicle or CV technology will transform our transportation world today. There are many features, for example, real-time alert, which helps the driver to avoid collisions. CV technology can help to reduce carbon footprint by using eco-lane, where motorists agree to drive at certain speed that conserves fuel. It will also help to reduce idling and unnecessary stop with Intelligent Traffic Signal, or ISIG, which is sponsored by US Department of Transportation, DOT. All these features will improve safety, productivity, and reduce negative environmental impacts. In 2010, US DOT started DMA, or Dynamic Mobility Application Research Program, and developed about 70 CV applications. Built on the success of DMA program. In September 2016, US DOT launched CV pilot program to deploy this system in Anthem, Arizona, Palo Alto, California, and New York. This presentation will discuss about Intelligent Traffic Signal System, ISIG, the security risk, and how to secure it before large deployment. The objectives are to identify security challenges specific to CV-based traffic control, why current design or implementation are vulnerable, and how to secure the system before nationwide rollout. Some assumptions made during research. The vehicle certificate system, developed by US DOT, can correctly authenticate all CV messages, so attacker cannot spoof sender identities in the messages. But the attack vehicle can spoof its trajectory data, for example, speed and location. The Security and Credential Management System, or SCMS, deployed by US DOT is sufficiently tested and not easily exploitable. Only one attack vehicle exists at an intersection. Attacker can compromise his own vehicle or other. Attacker is assumed to have limited computation power to launch the attack. The technology uses wireless connection to anonymously communicate with other vehicle, traffic signal, or other roadside infrastructure and mobile devices. The DSRC protocol is specifically designed for CV communication with dedicated band allocated by Federal Communications Commission, or FCC. To support this communication, the in-vehicle onboard unit, or OBU, needs to be installed on the vehicle, and the roadside unit, RSU, needs to be installed on the infrastructure. The OBU is periodically broadcast basic safety messages, or BSM. When CV vehicle is within range, they can perform vehicle-to-vehicle communication between them. Notification can also be transmitted from roadside infrastructure when a connected vehicle travels near the roadside unit infrastructure. With DSRC standard becoming mature, and the US DOT estimates the cost to install OBU around $350 per vehicle next year, This makes CV technology cost-effective and market penetration will gradually increase, as we see in this slide and the next slide. GATech is using high-fidelity data collected from vehicle-to-vehicle V2V and vehicle-to-infrastructure V2I wireless communications. It is operated at an intersection to control traffic signals and maximize flows in real time. As shown in the picture on the left, there are 8 traffic signals called phases. Phases with odd number are for left turn and others are for through lanes. Signal control is performed by setting light's duration and phase sequence. After green light time duration passes, the phase will be yellow for a short duration and then red before subsequent phase turns green. This is called the signal plan. The plan has 2 rings. Phases in the same ring are in conflict with each other, thus it will run sequentially. The phase sequence in each ring is broken down into stages, as shown in the upper right-hand corner. The phases in one stage are planned as a whole because they are in conflict with the phases in the later stage. The signal control algorithms needs to follow this rule. The goal is to reduce total delay for all vehicles at the intersection. BSM messages broadcast by vehicle equipped with OBU. These messages are signed using public key infrastructure so receivers can verify the signature before acting on it. BSM messages are received by Trajectory Awareness Component, which maintains the latest trajectory for each vehicle indexed by vehicle ID. It also assigns vehicles to the requested traffic light based on the intersection map. At the beginning of each stage, Traffic Signal Planning component pulls the trajectory data, sends signal control to controller, then listens to traffic signal status reported by the controller. The COP algorithm takes estimated vehicle arrival time at the intersection as input. It uses dynamic programming to calculate optimal plan with the least estimated total delay. Total delays are estimated using a queuing model. In the design, COP can plan unlimited number of stages. But in practice, with computation and memory resource constraints, COP cannot plan unlimited stages. Current COP implementation in ISIC system is first find the plan with the least unserved vehicles, then choose the one with the least total delay. Such planning limit unexpectedly leaves ISIC system vulnerable to congestion attacks. COP algorithm only optimizes the signal plan for equipped vehicles. Its effectiveness is greatly reduced when the number of equipped vehicles is below 95%. The market penetration to equip 95% of vehicles was estimated about 25 to 30 years. EVLS algorithm is used to bridge the gap before penetration reached this level. EVLS is algorithm used to estimate trajectory data of the unequipped vehicles. COP and EVLS were chosen by the ISIC designer, the team of signal control experts selected by US DOT. The threat model in this research are the attacker can compromise onboard unit in their own vehicle or someone else to send malicious BSM messages to roadside unit in order to influence signal planning. As mentioned in the assumption, the attackers cannot spoof the sender identities in BSM messages. This research is more interested in security problems specific to CV-based traffic control. This means the attack vehicles have to use their true identities to be able to send BSM messages. The BSM messages have to be signed and authenticated, but it will send spoof vehicle trajectory data. Data spoofing strategy. All incoming data is subject to geofence check. So the attackers need to perform reconnaissance to know the geographic location of a targeted intersection and only generate valid location data that will pass the check. Strategy S1 works both in a full deployment, where penetration rate reaches over 95%, or transition period where penetration rate below 95%. The attacker can add an entry to the arrival table. The arrival table is a two-dimensional array of arrival time and phases. Strategy S2 relies on confusing EVLS as it feeds into COP. As shown in this figure, the equipped vehicle data for each lane are assigned into three regions. The queuing region includes vehicles waiting in the queue with zero speed. Slowdown region includes vehicles slowing down because of the front vehicles, and the free flow region includes faraway vehicles travel at speed limit without slowing down, so they behave independently. The algorithm first finds the stop equipped vehicle that is the farthest from the stop line and uses its location as the end of queuing region. Among these three regions, the attack to queuing region is most effective. The attacker can set the speed to 0 and set its location to the farthest possible point of an empty lane within the geofence. Attack strategy. The most successful attack is to add a spoof vehicle trajectory with a very late arrival time. It is causing the green light end time for each requested phase to be extended or pushed out. As shown in this figure, due to spoof late arriving vehicle, the time for the green light of all phases in the first stage are extended in order to serve the latest vehicle arrival. In turn, it causes long delay to serve the vehicles in the second stage. The two-stage planning is highly vulnerable to late arriving vehicles, yet it was chosen by ISIC developers as the default value. The reasons behind this was because the runtime for more planning stages are too high in practice to meet the timing target. Due to hardware limitation on the RSU, using more stages will increase COP solving time. Meanwhile, they found two-stage planning total delay average does not have much difference in comparison with 5-stage planning. To address the problem before large-scale deployment, this slide shows some of defense directions. The transition period is more sensitive to data spoofing attack with current ISIC design. A massive congestion attack can be largely avoided when penetration rate is reaching 95% or more. It is inevitable to go through transition period until onboard unit is installed in each vehicle. It may take 25 to 30 years to reach 95% penetration rate. As introduced earlier, the COP algorithm is only optimal in full deployment period. During transition period, it's very important for the transportation and security communities to design effective and robust signal control algorithm. Due to performance limitation of roadside unit today, the ISIC has to use a suboptimal implementation of COP algorithm which allowing the data from a late vehicle arrival to influence the signal control. When given enough computation power, it is indeed very hard to maliciously influence the signal control in full deployment period. The performance improvement will enable planning more than 2 stages, ideally 5 stages. Such improvement can be both at software or hardware level. Another defense mechanism is to use infrastructure sensor where the attackers cannot easily control. There are vehicle detector sensors buried underneath the stop line to measure aggregated traffic information. Even though they are less useful in CV environment, they can be repurposed to help detect data spoofing. It is a cost-effective solution since they are already installed. If such aggregated data is not sufficient, other roadside infrastructure can be used to provide more informative data, for example, cameras. Some concluding remarks in this study. After performing security analysis on the emerging CV-based signal control and focusing on realistic threat model, we found the current signal control algorithm and signal planning configuration are highly vulnerable to congestion attacks. This attack can create massive traffic jams. This work is expected to inspire a series of follow-up studies, including but not limited to evaluation of different intersection sizes, traffic pattern, more robust CV-based algorithms, and concrete defense system. Thank you for your time and attention. Please post your questions and comments about this subject in Piazza.